All right, here we go. 8.5 exponential and logarithmic equations. This is it for chapter 8. So we'll wrap things up here. And so what are we learning today? We're going to solve exponential, and then we're going to solve logarithmic equations. So those are your two new vocab phrases, as well as with the change of base formula. So a couple skills checks to get started. So let's simplify this. Number one. Log base 9 of 81. How do we go from 9 to 81? 9 squared gets us to 81. How do we go from 9 to 3? The square root of 9, or 9 to the 1/2. So if we simplify that, that's simply 1. All right, so use the same type of thinking here on 2, 3, and 4. And when you're ready, let's keep going into 8.5. All right, so exponential equations, anything where we have a base, an exponent where the variable is in the exponent, and then equals a number on the other side. All right? So a couple things here. If a and b are positive and a equals b, then log base a equals log base b. So therefore you can solve each side by taking the logs of both sides. So here's what that means. Here's what we're going to do. To cancel out exponents, we're going to do logs. All right, so here we've got 7 to the 3x equals 20. All right, so what we need to do on this is to cancel out the 7, we're going to do, and where to go? It doesn't really look like it's up in the notes there, but we're going to say log base 7 on both sides. All right, because if we do that, log base 7 to the 7, with this 3x, remember the 3x could come out front, so now we have 3x times log base 7 of 7. And how do you go from 7 to 7 using exponents? This thing turns into a 1. So that cancels itself out, and we're just left with 3x equals log base 7 of 20. All right, so we don't know what that is yet because 7 doesn't go into 20 at all using exponents. We'll learn how to use the change of base to solve this shortly. But for right now, all we're going to do is just divide by 3 and leave this as our answer. Log base 7 of 20 divided by 3. All right, so see if you can use the same thinking for understanding check number 1. All right, so now we need the change of base formula here. So the change of base formula, and this is where we get to use our log button on our calculator. All right, because if we have log base b of m, we could rewrite this log base c of m over log base c of b. And why is that helpful? Because we have a log base 10 button on our calculator, so we could plug in log base 10 of m. We could plug in log base 10 of b, and then just divide the two on our calculator. All right, so that's how we do log problems on our calculator. So now, let's go ahead and take a look at this problem. Use the change of base to evaluate log base 3 of 15. All right, so that's going to be log base whatever we want of 15, the big number, over log base c, whatever number we want, but it has to match up, of 3, the base, the smaller number. And then we want to convert it to a logarithm in base 2. So it's saying for that, we're going to use base 2 here of 15 over log base 2 of 3. Okay? And so that's how our setup is going to go right here. And we can also, on this one, no, I'm going to pause it right there, leave it there for now. Okay? So we can convert those if we need to. You're up for understanding check number 2. All right, so solving an exponential equation by changing bases. So now that we have our change of base formula, we can solve this all the way through. So how do we get rid of the 2 right here? We're going to put a log base 2 in front of it. Equals 170. Oops, I forgot to do it to the other side. Equals, since I did log base 2 to the left, I got to do log base 2 to the right of 172. All right, so the log base 2 and the 2 cancel, and we're just left with 3x equals, and here's where we're going to change it. Change of base. Log base 10 of 172 over log base 10 of 2. So we're going to grab our calculator and plug that in. Log of 172, make sure you close your parentheses here, divided by log base 10 of 2. We get that, and then that equals 3x. So we need to divide both sides by 3 here to get rid of that 3. Go away, Java. Divided by 3. And we get 2.48. 2.48 is our answer. X equals 2.48. All right? And our job here is done. Your turn. Understanding check number 3. Okay, we can also solve exponential equations by graphing. So another way to do this. I'm going to grab the graphing calculator again. All right, so we can always solve equals problems by doing, clear, the left side as our y1. So I'm going to type in 6 to the 2x. And I'm going to type in for y2 the right side of the equation, 1500. Now I got to change my window here because I know I'm at least going up to 1500 for the y. So that's way bigger than 10 and negative 10 here. So let's change this to 1400 and how about 1600? And go ahead and graph that. There's the first equation, and here comes the second equation. And I want to know where they meet right here. So I got to zoom in a little bit so I can get a little closer. I'm going to do a zoom box. So I move my cursor until I get to the top left of where I want it. I hit enter, and then I move my cursor down and to the right to make a nice little box. And I'll hit enter again, and it zooms in just on that spot there. All right, so we want to figure out where these two lines are going to cross. Now we're going to calculate, so that's up here, second calculate, the intersection of those two lines. So where's our first curve? Where's my cursor? Keep coming. I know we want it to be closer to 1500. I think I just jumped there. Yep. Enter. All right. There's my second curve. And then where do they meet? Let's move over here. I want to put my cursor right where they're going to cross. Oop, too far. Come back. Hit enter. And they're going to intersect at 2.04 for x. All right, so x equals 2.04. We can do this graphically. We can also do it with the logs algebraically. So go ahead and see if you can solve this by graphing. Make sure you can figure out how to use your calculator to do the intersection of this equals this. All right, refer to the photo. I don't have the photo. Hold on a second. Let me go grab the photo for us. Okay, there we go. All right, so the photo, we've got ourselves some sheep here. We're looking at sheep populations. And here's the key. In 1971, there was 1,170 of them. And by 1999, only 335 remain. So, write an exponential equation. We know how to do that. Y equals AB to the x. And if the decay rate remains constant, in what year might only 5 sheep remain? So that's where we're going to do our new stuff here. So we know we've got ourselves in 1971. I'm going to make that year 0. We had 1170. And by 1999, so that's how many years afterwards? 99 minus 71 is 28. So year 28, we had 335. So y equals AB to the x. The nice thing here is that I know A is 1170 because that's my starting number. So y equals 1170, B to the x. Let's plug in our x's and y's from the other number. So 335 equals 1170 and B to the 28. And so calculators. Let's see, we're going to go 335 divided by 1170. And then we're going to take the 28th root of that, so 1 over 28. Okay, so 0.956 is our B. So there's our model, y equals 1170.956 to the x. You'll remember that 0.956 means we're losing about 4% a year, 4.2% per year. All right, so in what year might only 5 sheep remain? So in what year are we only going to have 5 sheep at all? So let's plug this in. 5 equals 1170.956 to the x. All right, so first thing we can do, we want to try to get x by itself. Let's divide by 1170. And I'll need the calculator for this one. So 5 divided by 1170 is that. So 0.004 equals 0.956 to the x. Now how are we going to get rid of the 0.956? We need to do log base 0.956 of both sides equals log base 0.956 of 0.956 to the x. And all this stuff cancels away and we're just left with x equals, we'll do change of base. Log base 10 of 0.004 divided by log base 10 of 0.956. And if we can plug this into our calculator, we're going to be in business. So log of 0.004, let me put in a couple extra decimal places, 27, what do we got, 35, divided by the log of, and it's up there above, 0.956, 3175. 122 years. So it's going to take a while, but eventually not a whole lot of sheep remaining if the rate of decline remains constant. All right, you're up here. Let's use some new numbers here for understanding check number 5. All right, now we're going to go the other way. We're going to get rid of logarithms. And this is fairly straightforward. It's just in reverse. Now we have to figure out what's our base here. So if it doesn't say anything, it's a 10. To get rid of log base 10, we're going to use 10 as a base of an exponent problem. These will cancel, and you've got 3x plus 1 equals 10 to the 5th. 3x plus 1 equals, that's a 1 with 5 zeros. 100,000. So we'll minus 1, which is 99,999. And we'll divide by 3, which, look at that, that's going to come out as 33,333. Nice round numbers on that one. All right. So, next up, understanding check number 6. And last one here. All right, so sometimes you have to use your properties, condensing and expanding, before you can get going, because we need to have a single logarithm to cancel it out. So let's first put the 2 up here. Remember, you can bring it up top. And then, what does the minus do? That means that we're dividing. So x squared over 3 equals 2. Now that we have it all condensed into a single logarithm, we can get rid of this. This is log base 10, so we can use a base of 10 to cancel them out. We'll have x squared over 3 equals 10 squared, which is 100. So x squared equals 300. So x equals square root of 300. 300 is 100 times 3. So x equals 10 root 3. Okay? And only positive, because you cannot do logarithms of negatives. Right? You can never do a logarithm of a negative number. And if we put in negative right here, that's what we'd be doing. So can't do that. Only the positive. All right. Finish things off with understanding check number 7, and your job here is done. Any questions? We'll go over it in class. Good luck.